We move on now to the third phase, which is mass manufacturing. This is the process of producing many product units or operating many system units using full-scale manufacturing facilities. Now, we went through the phase of product development, then the manufacturing planning. Now we're getting into the real things. A phase where some of the things which were very difficult to account for in the product development and the manufacturing planning may come up and they may represent further challenges for us. When you start producing thousands and the millions of units, then you get into issues such as people involvement, variability between one machine and the other, inconsistency on daily basis, distributions, logistics, coordinations. So mass manufacturing is the real deal here. And that is really where tools such as statistical process control, for example, which we'll discuss later on, become very, very important in this phase. The basic problem in mass manufacturing is maintaining consistent quality. All organizations face minimum challenge when it comes to meeting average or target average values. The difficulty, however, often comes from meeting a consistent product. Because the worst thing that can happen is to produce a product of high quality level this week and the low quality level next week. The worst thing that can happen is to have a product that exhibits variation from one shipment to the other. And that is the key challenge of mass manufacturing. Consistent quality levels of all manufactured units without sacrificing the rate of high volume production. It's a real big trade-off. Quite often the high production or the rush to produce massive amount of a certain product result in inconsistency. So how can you maintain the high volume production and meanwhile keep the product quality consistent is a real issue. That is where quality control really works the best. One has to realize the sources of variability associated with any process. In this course, and as is commonly agreed upon in most quality control applications, variability or sources of variability may be divided into two types. I call them level A and level B. Level A is the so-called common cause variation. These are, for example, the variation in the characteristics of raw material. Most raw materials come from natural resources or natural origins. And the natural and the nature means variability. So some of the raw material will exhibit inherent variability in its characteristics. So we have to deal with this variability. It cannot be eliminated because it's inherent. So some form of manipulation of this variability for the sake of producing a consistent product will have to be done. Other factors that are also common, it is what we call noise factors. Humidity, dust, machine vibrations. All of these are noise factors because they often happen in random fashion. Things can change. Some negligence here, some negligence there. or they can also happen due to the use of all the equipment or a lack of 100% maintenance program. So these are things that are likely to happen, and they are common. Quite often we have to deal with these by making the whole operation robust against the changes, because if humidity and dust and the vibrations are issue, then the question becomes of a choice. Should we actually go and redesign the whole process to make it totally robust against humidity changes, dust existence, or vibration? Or should we run an operation that can accommodate some of that, some of the humidity change, some of the dust, some of the vibration, yet perform at the acceptable levels? Another source or another reason for common cause variation is manual handling. Every time human touch things, variability is likely to be an expected issue. People are different in skills, different qualifications, different in attitude, different in behavior, different in self-discipline. And as a result of that, anytime human is involved in something, variability should be expected, and that goes under common cause variation. Now, level B variation is what we call assignable cause variation. These are gross variation caused during or by the people handling the operation, either intentionally or due to ignorance or negligence or laziness, lack of knowledge. And a key criteria of mass manufacturing process is to maintain the common variation within the design or specified tolerance limit. Dealing with common cause variation have to be done in the design and the product development stage. Assignable causes in an ideal operation should not happen, but in mass manufacturing they are likely to happen. As I mentioned, not all people are alike, and not everything will go the perfect way that we would like it to be. So common cause variation should be handled in the design. Assignable cause variation should be handled by continuous monitoring of the process and making sure that the causes by human, by negligence, by lack of maintenance, the gross problems are prevented. That takes us to one of the most commonly used tools in quality control, the control chart. The use of a control chart goes back to the early part of the 20th century, 1920, around this time. Schuhart is the developer of the control chart, and we will talk a little bit about the evolution of a control chart in later sessions. But if one would think about the fundamental basis of a control chart, one will find that it actually stems from basic statistical tools. Indeed, a control chart is a direct derivative of the so-called histogram. Here is a histogram that all people are familiar with. And the idea here is, in any process, the organization or the operation collects data every day reflecting the characteristic or the values of the characteristics of interest. Producing metal sheets is the thickness of that metal sheets every day. Producing textile fabrics is the weight of the fabric, the strength of the fabric, And on daily basis, you collect a lot of data. And one can imagine that in every day, we're constructing a histogram such as the one that we see here, where it is more or less normally distributed, where you have few of the low values, few of the high values, and plenty of the middle values here. Now imagine that every day we construct a similar histogram. So every day we go to the process, collect the data, construct a histogram of this data, which will have a center very much the same as the center of the data. And you can see here from one day to another, the center keeps changing, okay? And we can replace the center by a point or the average values of every day. And we converted that into a two-dimensional graph. We call it the control chart. That is bounded by limits. So here you have the upper limit, the lower limit, and we can then profile the process as it go up and down and look at some of the points that goes outside the specified or the control limits as we will define it later on. That is the simplest way to put the control chart concept in perspective. It's a result of collection of data on daily basis, and this collection is a group of data from which a histogram is formed, and we're monitoring either the center of the histogram, or we may be monitoring the spread or the width of the histogram. In this case that you see here, it is the center of the histogram that we are after, which goes up and down from day to day, or shipment to shipment, or week to week. And in this sense, the control chart is examined on a time domain, meaning the horizontal axis of the control chart may be week 1, week 2, week 3, and so on, or it may be day 1, day 2, day 3, or it may be shipment 1, shipment 2, shipment 3, and we're looking at our performance on daily basis. And based on preset limits or control limits, as we will describe it shortly, we can see if our process is within the limits or outside the limits. So those limits that you see here with the arrows, those dotted lines, are extremely important because these are the boundaries within which the process should be maintained. Outside these boundaries, such as this yellow portion here, means that the process is going out of control, and within these boundaries means that the process is going in control or operating in control. And here you can see the center line as we wish it to be, which is right in the middle between the two control limits. Obviously, in order to use a control chart, one has to collect data. Every day we collect a lot of data. And one of the major headache in today's operations is the flood of data generated every day. Lots of data going in, lots of data going in. Control chart is a way, a very simple way, to look at all of these data at once without too much details via a simple profile. We call it the control chart, in which we have control limits upper and lower, and we have a center line, and we're monitoring the profile of the process from day to day, week to week, or shipment to shipment. This is a tool that everybody can understand. It's not so difficult to tell the operator of the machine that if your points are going outside the control limits, that means there is something wrong going on with the machine or the process in question. Here is a two-dimensional graph that we call a control chart. The horizontal axis is time, perhaps a location if we're comparing between different control charts in one plant or the other, the center line, the upper control limit, and the lower control limit. Now notice early on we introduced to you different types of limits. We introduced to you the design limits. We also introduced to you the specified limits, which we said that they are driven by the customers very often. The upper and the lower control limits are different than these two types of limits we introduced earlier. The upper and the lower control limits stem and derive from the data that you produce. So when we set an upper control limit and the lower control limit, we don't use external sources. No, we use the actual mass manufacturing data that we make. So everything here is a reflection of our own doing. The center line represents the actual average over many days or many weeks. The upper and the lower control limits represent the upper and the lower statistical limits dictated upon by the process, by the actual data, as we will see later on when we discuss how a control chart is constructed. We monitor the process on a daily basis, and remember, each one of these points is not necessarily a single point, but it's the center of a histogram or a sample or a subgroup, as we will call it later on. So we really going to have to trust each one of these points, because it's not just a point, it can be a result of many data that we collected in this particular day or this particular week, and this is the summary or the average of this data. All points within the control limits are said to be in control or in a state of in control. Recall what we said early on about the different categories or the two main categories of variability or sources of variability: common cause and the assignable cause. So all the points within the limits will be categorized as due to common cause. When you see a chart like that, the reason we are accepting the variation within the limits, the ups and downs, is that we believe in the role or the law of nature. And the law of nature is the law of variability. Obviously, we would love that all these points will lie on the center line, meaning producing the exact same thing every day. But I wish life or the real world is that easy. So we have to accept some tolerances. We have to accept some variabilities, and we call this common variability or common cause variability, either due to the fact that they are inherent, natural, we cannot do much about it, or due to the fact that it's so costly to minimize them or eliminate them. So only when we have a point out of control that we describe as an assignable cause variation. Why? Because this point do not belong to our inherent process data. It's something that happened later on due to negligence or a gross problem in the shipment or the process of that day or that week. And the point outside the control limits, as a result, will be called an out of control or assignable cause variation point, and the actions have to be taken, hopefully on timely fashion, so this point will be eliminated or it will not repeat, so the process can go back to the stable within control limits condition. In the context of quality control, the link between the three basic engineering activities that we mentioned so far, which are the product and system development, the manufacturing planning, and the mass manufacturing, is quite important. Reduction of common variation through appropriate production and system development, because we told you that all of these common variation are results of inherent variabilities. And we also told you that the only way to overcome these common variation or reduce it will be via a redesign of the process or going back to the initiation process and try to minimize these variability either by selecting a different material or selecting a different manufacturing scheme that will result in reducing these common variation. That is where the role of product and system development is all about. They may also be a result of deficiency in the manufacturing planning. Okay? So as a result of that, the manufacturing planning phase is a crucial phase, because a lot of what we do in the manufacturing planning and before we go to the mass manufacturing can lead to minimum common variation. The mass manufacturing, however, should strictly be related to the to the assignable cause variation, because these are things that can only happen after we start the mass manufacturing. So overall, in linking these three basic activities that we discussed so far, we have to keep in mind that it's very important to reduce common variation via product system or system development and via manufacturing planning, and maintain low process variability during the manufacturing planning and going through the mass manufacturing. Quite often, we do a product development to enhance an old product. So we have an existing product that does not perform very well in the marketplace, and now, or we have a process, a machine that's not functioning right, and now we're trying to redesign our process or reselect our material to reduce variability. That is a way to reduce common variation. Here is an old process with high variability, high variation, many red points, and as a result, the process is stretched out, which may not be very good for the customer or for the product image and the performance. And now we're going to replace this with a new process. And as you can see here, as we make that replacement, as we move from the old process to the new process, we're establishing new limits here. Remember, those control limits are results or reflection of the process. These reductions in the common variability can only be achieved during the product development or the manufacturing planning stage, or during both activities. This is a very important issue, because if you get to the mass manufacturing phase, then most of the common variation, most of these ups and downs that you will see will be a done deal that you cannot do much about it. That takes me back to the point that I made early, that most reoccurring problems are results of design deficiency, of failure to minimize common variation during manufacturing planning or production and system development. Later on, we'll discuss more about that. We'll move on now to the final phases. We developed the product. We planned for manufacturing the product. We went into mass manufacturing, where we used some quality control tools, such as the quality control chart, to monitor the process. And now we're getting into the problem solving phase and monitoring the processing performance phase, which really the control chart was an essential part of it. Why do we need to monitor the process? Obvious reasons: to ensure that the process continues to run in a state of in control, to ensure that process variability always fall within the design and or specified limits, to monitor particular improvements in the process. Sometimes we have to make some readjustment in the process, and we would like to see if these readjustment have resulted in improvement, and that's why we have to monitor on continuous basis. So monitoring will always become an essential part of quality control. Now, problem solving is something that one would wish that we don't have to deal with, but problems will happen, always. And this is an issue that everyone should be involved in. One of the problems associated with problem solving is the lack of systematic way to deal with problems. Now, if you work in any company and you face a certain problem repeatedly, and you realize that every time the problem happens, you rethink and redo as if you've never gained any experience from the occurrence of the problem previously, then you really have a problem. And this problem is essentially a lack of systematic way to approach problem solving. Starting with the first phase of problem solving, problem identification. The reason we fail to solve many problems sometimes is very simple. We failed to identify the problem, either because of the problem is subjective or because we did not brainstorm enough to identify the problem. Part of the identification is not only to describe the problem in stated words, such as we have too many rejects, or we have off-target machine, or we have slippage in some of the belts, but also to quantify the problem. Meaning we have to have data that are monitored and recorded to give us a good idea about the magnitude of the problem. Because a problem that is not well stated and then well quantified is a problem that's likely not to be resolved. So first phase is to identify the problem. Second is to be able to quantify the problem. Hopefully you already have some data monitoring and the recording system that can give you quantified and objective ways to measure the magnitude of the problem. Third is to analyze the problem causes, which require a great deal of brainstorming. People have to get together and look for the different causes of the problem. Typically, for a given problem, one can list a very large number of causes, especially if we don't know much. Every person involved in one aspect of the production of the product may come up with one or two or three causes of the problem, often from their own area of expertise, or to blame other people on the problem, saying, well, I did not do it. It may be due to the process down the stream of operation, and he may come up with a reasoning for that. Analysis of problem causes. We should not get into this phase trying to put causes to the problem without first identifying the problem and being able to quantify or put the problem in a quantitative and data format. We analyze the problem causes, and hopefully based on this analysis, I just mentioned that there may be many causes, but in almost every case there will be only one or two causes that are directly leading to the problem in hand. One of the reasons for that is just the nature of any problem and the fact that it came about in random fashion or suddenly. There must be one or two main reasons, main causes. We can mention the 100, but it's often the case that there is one or two of these causes that's directly influencing the problem. It's also the fact that causes are often independent, meaning one cause leads to the other. And if we succeed in our problem cause and effect analysis, then we very much will succeed in correcting the problem. And that is the fourth phase of problem solving. At this point, we solved the problem. Did we really solve the problem? So we have to pose a very important question. After solving the problem as we thought it was, as we identified it, as we monitored it, as we specified the causes, after we correct what we think will lead to an improvement, did the process actually improve? We have to address this question immediately. And if the answer is yes, then it is very, very important to document not only the improvement, but also what we did in each one of these phases to reach the improvement. The importance of that is, if the problem reoccurred for one reason or another, then we don't re-scramble and go through these phases and deal with the problem as if it's a brand new experience. Documenting the problem, documenting the actions, documenting the causes is an essential process of problem solving. Now, if the answer is no, that means the process did not improve, then we need to recycle all of this. Then we need to go back through this systematic cycle. Was the problem clearly identified? Remember, this is the first phase. Did we truly identify the problem clearly? Or maybe we refer to another problem? If the answer is yes, then great, we need to seek the second issue here. Did we monitor it? If the answer is no, then we need to go back to the problem identification phase and try to re-identify the problem appropriately. Again, if we come up with the same identification, or if we know or believe that the problem has been identified correctly, then we need to go to the next step. Our major causes have been identified. You see, we're revisiting the cause and effect analysis again. What if the answer is yes? What if we came up with the same causes? Aha, that is yes answer. Then we're going to have to follow a non-traditional way of correcting the problem. One would hope that we will not get to this phase, because quite often, if we try to solve a problem and we found out that we clearly identified the problem, and we found out that we clearly identified the causes, yet our corrective actions did not yield an improvement, quite often the case is a design deficiency, a very costly alternative to solve the problem. Phase 2 means design, product development, product enhancement, because apparently all the traditional corrective actions resulted in a poor solution or no improvement in the process. That's the worst case scenario. This case study is very interesting. Quite often, when we fail to solve a problem after identifying the problem correctly, monitoring the problem, identifying the causes that affect the problem, and take local corrective actions. If the problem or the process is not improved or did not improve as a result of all of that, quite often we seek expensive options. Quite often we buy new machinery, perhaps different humidity or environmental control systems, different oven system, different material that is more expensive. All of these are very costly options. Before we seek one of these very costly options, it is very important that we entertain our intelligence. Intelligence or personnel intelligence is the most important assets in any company. It's in these situations where problems occur that you can really test your organization and your company of whether you succeeded in hiring or using the right qualification people or not. This is a typical example, the so-called mismatch of ceramic tile manufactured by a tile company. This company produced ceramic tiles of exact dimensions, and as we know, those ceramic tiles must fit. You cannot have a tile that's large and the other one is small, otherwise you will have a mismatch and you will have a real problem. And quite often if you have a mismatch, that means you cannot do your design, and any mismatched tile will be rejected, rightfully so. A real problem that happened in tile companies. Now this case study is interesting. It's actually a real case study that resulted in a whole concept of quality control. We call it quality engineering, as pioneered by Genish Tagoshi, and we will talk about him later on, a Japanese engineer. Remember the phases of solving the problem. First, we have to identify the problem by making a problem statement. Okay, the problem statement is frequent complaints from the customers, of course, concerning many ceramic tiles failing to fit in the design due to differences or variations in dimensions. That's an obvious problem here. Mismatch. You put your tiles side by side and here you go. 1 or 2% of the tiles mismatch or do not fit or have different dimensions. Like this situation here. This situation is totally unacceptable, because now you're going to have to look for a tile that fit into this dimension, and you're going to have to take this tile back to the company. By the way, this particular company was doing extremely well. It's a millions of dollars company, and they were dominant in the market. They have the largest market share, and they had a newcomer, a competitor in the market that was slightly threatening their existence. Now, the last thing you want to have when you have a pressure of competition is to have a problem that is as obvious as this one. That is inconsistency. Now, luckily, the company realized the problem in advance. Why? Because the company implement a reasonable quality control program. They always measure, and they know their target value, the area of the tiles. They know their control limits, or the minimum and the maximum values, or the tolerance. And they do know that, and they do monitor that on daily basis. They know the standard distribution, how it looks like. They know the target. They know the allowed tolerance. And their products was following all of that for many years. Now, all of a sudden now, they having a new process. You can see here the distribution has stretched out. The target value is still the same, average area, but we have some ceramic tiles that were larger than the upper limit, and the other ceramic tiles that were smaller than the lower limit. From 100%, that's the whole distribution, meeting the standard requirement, to only 60% of the distribution meeting the desired requirements or the specified requirements or tolerance, and that is not accepted. The company also implement control charts. Early on, that is how their control chart looked like. Here is a target area. Here is the upper and lower, which I exactly met the specified limits. And you can see here these points which represent the area of the ceramic tiles were very close to the center, meaning the whole process was running very, very consistently. When the problem began to start, that is what happened. Points are all over the place. Many points are outside the control limits. Now, the ideal situation is to discover the problem very early. Definitely in this situation, you cannot ship tiles that have points outside the control, on the lower or the upper side. But the point I'm trying to make here is that in order to detect the problem, you have to have monitoring and the quality control system in place. If it wasn't for this approach, which is a statistical approach, and if it wasn't for this approach, which is a quality control approach, which has statistical basis, the company may have waited so long and waited for customer rejections. And the last thing an organization wants to have is realizing the problem as a result of a consumer or customer realization of the problem. That's the difference between the proactive approach, is looking at our process and see if there are deviations from the target values, versus waiting until the consumer or the customer complain about it and then having to do something about it under tremendous pressure. In relation to the concept we mentioned earlier, which is modified slightly here as the ratio between the control limit and the specified limits, this company has a capability of 1 at this situation. Here, the capability went far below 1, meaning this company is in trouble, design and development and the mass manufacturing wise. So what's the next phase? Well, the next phase is we brainstorm. All personnel involved in the ceramic tile making have to get together. And that is the cause and effect diagram of the mismatch tile. And we're going to talk about cause and effect in more detail later on. But you can see that the cause and effect diagram is a very simple. The main axis of the cause and effect diagram point at the problem, which is the tile mismatch, the area variation. The branches of the cause and effect diagram point at some of the main causes. For example, incidental breakage. Of course, that's a thought or a cause that may be viable or not. Chemicals, environmental factors. And under each main cause, there may be some sub-causes. For example, if we say environmental factors, then the question will be, what do you mean by environmental factors? Well, that can be variation in surrounding media, temperature, humidity, and so on. If we say chemicals, then the question is, what do you mean by chemicals? Yes, that may be concentration, the mixing of the ingredients of the components required to produce the tiles, and so on. If we say incidental breakage, that means mishandling of the tiles as we transport or remove the tiles from one operation to another. Stacking problems, we put the tiles on top of each other, some of them break, some of them don't. Some of them are shipped for some reason. Or they may be system failure, they may be calibration issues. You can see here that we are exploring different causes of the problem. We don't yet know the main cause. We're just exploring. Which brings about a very important issue. This problem should have been anticipated in advance. Meaning we don't wait until the problem happens to develop a cause and effect diagram. Always when you have a process and you are making a product, you need to have some form of anticipation to some of the problems that are likely to happen as the product is in use or after shipping. And if you have this anticipation, then you will have a ready-to-use cause and effect that you may fine-tune it, adjust it, that you can put in the table that explains or explores most of the potential causes of any problem. We'll discuss that later on. After some time brainstorming, the group that involved all personnel, they came with a number one reason, and that was temperature variation. Tiles are made in an oven under very precisely controlled temperature environment. And the variation in the area was found to be a direct result of the variation in the temperature. Now, every time you have a problem with controlling the environment, temperature, humidity, dust, then you really have a problem, because the options before you become very expensive. Indeed, the obvious options before this company was changing the temperature control system, having a completely different environment, which can cost millions of dollars, as they came to find out. And the more seriously, the results may not be guaranteed, due to maybe just a matter of time before the problem reoccur, or inevitable deterioration in the temperature control. So we have a real problem here that is threatening this company to go out of business and leading to another competitor to take over the market share. These are serious problems that need to be handled. Again, brainstorming is a process in which a group of people get together, each in his area of expertise, come up with a reason, and list the reasons or the causes as we mentioned. Obviously, this company followed the routine procedure of problem solving. They identified the problem. They monitored the problem even in advance, so they realized the problem before the customer realized it. They brainstormed the cause and effects, and they came up with the conclusion that the problem was primarily a result of temperature variation. So they have done their homework every step in the way of the problem solving flowchart. The only problem is they could not take a corrective action, because if you have a problem such as temperature variation, the option is to replace the system completely. So they really had to move quickly to phase 2 that I mentioned earlier, which is the more costly phase, because it is a redesign or redevelop a product or a system. So they evaluated the current design criteria to seek opportunities to improve the current design, because now they realize that the magnitude of the problem is so large that it cannot be corrected temporarily, or it cannot have a temporary solution that will eventually result in reoccurring of the problem. So in seeking the different options, they have to also consider the cost analysis. As I mentioned a minute ago, one of the obvious option is to change the temperature control system, put another control system. And that option was actually on the table, except that they realized that it will cost millions of dollars, and even with that, there is no 100% guarantee that the problem will be eliminated upon using a new temperature control system. So the temperature control system, although it looks like the most obvious one, it was not a cost-effective plan. So it was rejected. So they start thinking about other options. And one of the options was design modification. So in other words, instead of altering the temperature control, let us look into the process, okay, with a toothpick and analyze what can we do. What they found out was that one of the ingredients of the ceramic tile was a chemical that is very highly sensitive to the temperature variation. So all of this variation in dimension was not due to all the ingredients or all the chemicals in making the ceramic tile, only one component. So when we say design modification, we basically talking about, can we alter this ingredient or this chemical by another chemical that is less temperature sensitive? And that's exactly what happened. This company solved a problem that otherwise would have cost millions and millions of dollars by using an alternative ingredient in the ceramic tile chemicals that was much less sensitive to temperature variation. This led to the concept of the so-called robust design. A robust design is a design of a product or a system in which the system or the product is largely insensitive to noise, often uncontrollable factors or variations, such as temperature in this case. Robust design. We talked a great deal about robust design in the design of experiment chapter in the statistics course. Let me finish this chapter or this session by a very important slide. If we look at any organization, we will find that there are two types of organizations, divided or categorized by the percent of involvement of the personnel of the organization in the different basic activities of engineering that we mentioned in this chapter. One category will look something like this, where most personnel are involved in product development. This is where the brain, this is where the effort, this is where creativity, this is the true gain, the true investment of a company in its personnel and its own people. Because if your company has a large involvement in this, then more than likely it will have very lesser involvement in the problem solving phase. If the product is developed appropriately or properly, then you may not have to do as much problem solving. And what does that mean? It means taking the personnel that are supposed or will be involved in problem solving into the product development phase, making a better use of the personnel. If your company is following this trend, then your company is doing great. If on the other hand, your company follow this pattern, where minimum involvement in product development and the very high involvement in problem solving, which means all resources, personnel, money, effort, tasks, time, equipment, are devoted to solve the problems. Yet we're doing minimum effort in product development as a result of allocating most of our personnel to the problem solving, then your company is doing bad, and this company is likely to go out of business and not able to compete. You notice that the intersection of these two curves is mass manufacturing, or what we call it job number one. Indeed, you could have two companies that have the same number of personnel, yet perform significantly different in the marketplace, producing the same product. And the reason for that is that one company is very busy problem solving, while the other company is very busy developing products and putting new exciting ideas in the marketplace to keep the stimulation and to keep the attraction of the consumer and the market. This chapter was simply an introductory chapter in which we reviewed some of the basic activities performed by engineers or engineers and the other personnel in a typical organizations that produce a product or manufacture a system. Next chapter, we will go into further details and start the phases of what we call integrated competitive quality program. Thank you. We'll see you next session.